Hello dear students. Today we will be looking at the topic extension of range of PMMC instruments. So this is a simplified diagram of a PMMC instrument. Here you can see that IM is a permissible current through the meter and RM is the internal resistance of the this particular instrument, and this is the total representation. And this internal resistance of the meter will be including the hairspring plus the coil arrangement, and then you have the second hairspring. Okay, so entire resistance uh, will be included as the internal resistance of the instrument. And in the last lecture you had already seen that the maximum allowable current through the meter or through the PMMC instrument is 20 milliamperes, because you have very fine or thin spring which is attached here, and this spring will be allowing you to send only 20 milliampere through it. If more current is being passed through this particular arrangement, it might burn out the spring or burn out the entire arrangement. So here you have a limitation of the current that can be flowing through this particular instrument. Now the internal resistance is given as R, and in the last class you had already seen that you are able to measure up to 100 amperes. Okay, you are measure up to 100 ampere current. Though your permissible current through the instrument is 20 milliampere, you are able to measure up to 100 amperes. So how are we able to do this? So this is being dealt in detail when under the topic extension of the range of instrument or increasing range of instrument. So while a PMMC instrument is used as an ammeter, you need to send some extra current through some other mechanism, and which is known as the shunt resistance. So here you can see that IM is the permissible current through the instrument, RM is the internal resistance of the instrument. Now you are providing a shunt resistance which is of a lower value. Now what happens is that once I is a current that is to be measured by the ammeter, once the current I is applied, IM will be flowing through the instrument, and rest of the current, that is I minus IM, will be flowing through the shunt, so that only say 20 milliampere will be flowing through the meter, rest of the current will be flowing through the shunt, so that your meter will not be damaged, and also you are able to measure the current. And RSH is the shunt resistance, and I is the current to be measured by the ammeter. Amperes, 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 amperes. And you will also have a range from 0 to 10 amperes. Okay, then you'll have another scale from 0 to say 50 amperes. So a single meter can read all the three, though it is able to send only 20 milliampere through this particular setup or the moving setup. So this is how you indicate the reading. So these are all calibrated scales, so corresponding to half the deflection. When you are moving, when the pointer moves from 0 to half your deflection, middle part of your the maximum middle part of the scale, in this first scale you will be reading 2.5 amperes, the second scale you have 5 amperes, and in third scale you will be reading 25 amperes correspondingly. So the scale is calibrated in such a way that it will be reading different values. Now how will you calculate or how will you find out that this particular range of the instrument? Now it's very simple. You are equating the voltage across these 2 points, A dash. Okay, so that is the simplest method to do it. So that is IM into RM. IM is a current flowing through this branch, so IM into RM will be giving you I minus IM into RSH. So when you equate that, you will be getting, or you can solve for RSH, because you know the value of IM, that is current through the meter, you know the internal resistance of the meter, you are also given the current that is to be measured by the instrument, and also this is also provided. So RSH is the only unknown quantity, so you can easily measure RSH. The multiplication factor is defined M, which is given as I by M. I is the current to be measured by the meter, and IM is the permissible current through the instrument. So which can be derived as 1 plus RM by RSH. So once you know the RSH, you can easily find out the value of multiplication factor. Now if you are given multiplication factor, you can find out RSH, that is the shunt resistance, using this equation, that is RSH is equal to Rm by M minus 1. So this also can be derived from this particular result. Now the range of the instrument, the ammeter, can be increased by reducing RSH. Once RSH value reduces, more current is allowed to flow through this shunt. So if you are planning to increase the range of the instrument, if you are planning to increase the value of 5, you can decrease the value of RSH, so that more current will be flowing through this, and a fixed value of current, which is a permissible value, will be flowing through the instrument. And the maximum value of current measurable using this setup is 100 amperes. Now this PMMC instrument, you have different values of resistances available, shunts available. So depending on the value of shunt we choose, we can measure different currents. So this is a meter resistance or internal resistance of the meter, and these are different values of shunts provided. So here you can see that in this particular instrument you have different ranges available. So you have 0 to 50, then you have 0 to 20 is available, 100 is given. Okay, then you have provision for measuring 10 ampere also, 10, 20, 50 and 100. Okay. All the four can be measured using the same meter. So once you are trying to measure 100 amperes, what happens? The shunt that will be used will be the smallest one. So R100, the shunt for R100 for measuring 100 ampere will be the smallest when compared to the shunt for 50 and shunt for 10. We'll take up this particular example. A DC ammeter has a resistance of 0.1 ohms and its current range is 0 to 100 amperes. If the range is to be extended to 0 to 500 ampere, then the meter required the following shunt resistance. So you are asked to find out the value of shunt resistance RSH. So Rm is given as 0.1 ohms and Im is given as 100 amperes. Suppose the meter is currently reading 100 amperes and you are asked to find out the shunt resistance if the meter range is to be extended to 500 amperes. That is a conceptual question. If it is the range is extended to 500 amperes, what will be the shunt resistance? So equating the voltage across the entire setup, A dash, so you'll have Im into Rm, which will be equal to I minus Im into RSH. So you can see that if you are having 100 ampere flowing through this path and you have 500 ampere reaching here, you will have 400 ampere flowing through the shunt. So 400 into RSH will give you 100 into 0.1. So from this you can calculate RSH is equal to 0.025. So if you are planning to increase the range of meter from 100 ampere to 500 ampere, you have to include a shunt resistance of 0.025 ohms. Now this is another example. A moving coil ammeter has a fixed shunt of 0.02 ohm, the coil resistance of 1000 ohm, and has a potential difference of 500 millivolt across it. So first we will just draw that figure. So we have a meter, this is R, this is the shunt resistance. Now your R is given as 1000 ohms and your RSH is fixed and the value is 0.02 ohms. Now you have a full scale deflection being obtained, and it's also given that you have a potential difference of 500 millivolt across this. So once you know the potential difference, you can easily calculate the current that is flowing through these two paths. Now ISH is given by 500 millivolt divided by the shunt resistance. So this is ISH. So that will be 25 amperes. Now how will you calculate IM? IM will be given by 500 millivolt divided by 1000 divided by 1000 ohms. 1000 ohm is the meter internal resistance or Rn. So that will give you 0.5 milliampere. So this is a current that is permissible through this particular moving system or through the coil or through the spring. Now you have to find out the current through the shunt that you have already found out, that is to what shunted current does it correspond to. So in this setup corresponds to 25 ampere of shunted current, ISH equal to 25 amperes. Now you have to calculate the value of R to give a full scale deflection when the shunted current is 10 amperes. Suppose you are reducing the shunted current to 10 amperes. Okay, so instead of 25 ampere, now you are only sending 10 amperes. Now what can be the change in R, internal resistance of the meter? So if you are given an option to change the internal resistance of the meter, what will be the new value of Rm? That is to be found out. Now since the shunt is fixed, we can calculate the voltage across shunt once the current of 10 ampere is passing through it. Now 10 ampere is flowing through the shunt, so the voltage across the shunt will be 0.2 volt. 10 ampere into 0.02 ohm will give you 0.2 volt. This 0.2 volt will be applied across this resistance, which is already carrying a current of 0.5 milliampere. Now the resistance of the meter for current of 10 ampere shunt will be given by 0.2 volt, which is across it, divided by the resistance, divided by the current, that is 0.5 milliampere. So that will be giving you 400 ohms. So initially you had 1000 ohms, now you have only 400 ohms. Now instead of 10 ampere, if you are going to or planning to pass 75 amperes through the shunt, so the voltage across shunt will be 0.02 ohms into 75 ampere will give you 1.5 volt. This 1.5 volt will be applied across Rm. Rm is unknown now, and 1.5 divided by 0.5 milliampere, which is the current through the Rm. So that will be giving you 3000 ohms. So in the third case, you have 3000 ohms as the meter resistance. Now next case, with what value of R 40% deflection obtained with I is equal to 100 amperes. That is, you have a 40% deflection is obtained with current equal to 100. So here you have current equal to 100 amperes. Okay. Now 40% deflection is obtained with current equal to 100 ampere. Now the current required to give full scale deflection. So for a meter, 40% deflection is obtained and the reading is 100 amperes. Now what will be the full scale deflection? That will be, since this PMMC has a linear scale, you can directly divide by this percentage deflection. So you'll have 100 divided by 0.4 will give you 250 ampere as the full scale deflection. So you'll have 250 ampere current that is flowing through this particular meter. So I is the shunt current which is being specified right now. It is not this current, this is a shunt. ISH is given as 100 ampere. So there is not much variation here. So if you are planning to send 250 ampere through the shunt, what happens? Voltage across the shunt will be 0.02 into 250, which will give you 5 volt. And 5 volt is now applied across this particular meter. So your resistance will be 5 divided by 0.5 milliampere, which will give you 10 kilo ohm. Okay, so kindly go through the discussion once again if you are not able to understand it once on the go. So it's not a difficult one, you can easily understand it. Now PMMC instrument can also be used as a voltmeter. While using as a voltmeter, what you need to do? Already the PMMC instrument is able to have some voltage across it, some minimum value of voltage across it, depending on the resistance value. The extra voltage has to be shared with some other resistance, which is known as the series resistance or multiplier resistance. So IM is a permissible current through the instrument, Rm is the internal resistance of the instrument, Vm is a permissible voltage across the instrument, which is the maximum value of voltage that can be applied across this particular moving system, including the pointer, including this spring, and V is a voltage to be measured, the total voltage to be measured by the voltmeter, and RC is the resistance which is connected in series or the multiplier resistance to limit the current. You have to limit the current to not exceeding a particular value. Now Now the current through these two resistances are same. So Im will be given by Vm by Rm. So this is the permissible voltage across the instrument Vm by Rm, which is same as V minus Vm. V is the total voltage to be measured. V minus Vm by Rsc. V minus Vm divided by Rsc, which gives you the current. So you are equating the current Im through the instrument. Vm divided by Rm equal to V minus Vm by Rsc. Now multiplication factor is defined as, so from this equation you can calculate the value of Rsc, since V, Vm and Rm are known, Rsc is only unknown. So you can easily calculate Rsc. Now the multiplication factor is given by V by Vm, which is 1 plus Rsc by Rm, which can be calculated from the above or derived from the above equation. And Rsc from this can be calculated as Rm into m minus 1. So if you are given multiplication factor, you can easily calculate Rsc if you are given Rm. Again, M is V by Vm. V is the voltage to be measured by the voltmeter, and Vm is the permissible voltage across the instrument. And the range of the voltmeter can be increased by increasing the shunt resistance. If you are increasing the shunt resistance, more voltage will be coming across this. So you can increase the range of this particular voltmeter by increasing the resistance of the shunt. The maximum allowable voltage which can be measured using this particular setup is 600 volt. Now just as the case of in the case of ammeter, you have multi-range voltmeters available. So here this is a common terminal. 30 volt is being measured here. You have 75 volt, you have 150 volt, and you have 300 volt. So your shunt series resistance of 300 volt will be the highest when compared to 150 volt or 75 and or 30. So once you increase the value of resistance, you can increase the range of the voltmeter. Now these shunts and multipliers are to be made of constant temperature coefficient materials, that is, they should not be affected by the variation in temperature. So they generally are made using constant and or magnanime kind of materials. So such type of materials are considered to be constant temperature coefficient materials, that is, their resistance will not change with respect to variation in temperature. Now we will take this example. A moving coil instrument has a resistance of 5 ohm internal resistance and gives a full scale deflection of 10 millivolt. 10 millivolt. Show how the instrument may be used to measure a voltage up to 50 volt and current up to 10 amperes. Now the full scale reading of the meter is 10 millivolt with 5 ohms. So you can easily calculate the meter current through the meter, that is 10 millivolt divided by 5 ohm, which will give you 2 milliamperes. So this will be Im. That is, you have meter here and you have this is Rm. So voltage across this is given as voltage across this is given as 10 millivolt. So you have 10 millivolt across the meter, and the current through the meter can be calculated by using this equation, 10 millivolt divided by 5 ohms. This Rm is given as 5 ohms resistance of the instrument, or internal resistance of the instrument, Rm. So the current through the instrument is given as or obtained as 2 milliamperes. Now for measuring voltages up to 50 volt, we need to connect multiplier resistance Rsc in series with the instrument, that you know. Okay, so we have only a range of 10 millivolt, so you are asked to find out the value of Rsc. So the equation is simple. You have one equation here, Rc is equal to Rm into m minus 1. That is a direct equation that you have. Or if you do not remember the equation, you can simply equate Im values. So you are trying to connect Rc. So the voltage here will be V minus Vm. So Vm is 10 millivolt. So Vm divided by Rm, which is already obtained as 2 milliampere, which will be equal to V minus Vm. What is V? V is a voltage to be measured, 50 volt. 50 minus Vm is 10 millivolt divided by RC. So RC is unknown, so you can easily calculate the value of RC. Now again, the same instrument may be used to measure current up to 10 amperes. Now the instrument setup is able to measure, so this is 5 ohm and this is able to measure 2 milliamperes. Suppose you need to measure 10 amperes. So what you need to do? You need to connect a shunt in parallel to the meter. So here you have trying to measure 10 amperes. So 10 minus 2 milliampere will be flowing through the shunt, and you have to find out the value of RSH. Now you can equate the voltage across these 2 points A dash. So what you will get? You will be getting this as 2 milliampere into 5 ohms equal to 10 minus 2 milliampere into RSH. So RSH is unknown, so you can calculate the value of RSH and see whether you are getting the answer. RSH is 1.002 milliohms. Okay, some value. Maybe another question. An analog voltmeter uses external multiplier settings with a multiplier setting of 20 kilo ohm. This is not watt. 20 kilo ohm. It reads 440 volt, and with the multiplier setting of 80 kilo ohms, it reads 352 volt. For a multiplier setting of 40 kilo ohm, the voltmeter reads dash volt. So you need to find out the answers. One of them is the correct answer, so it is left to you to solve. So hope you have understood how we are trying to extend the range of these instruments. So thank you.